Hi, my name is Beth Barabal, and this is a pre-recorded presentation for the 2021 Society for Mathematical Psychology Conference. Before I get into the core of the talk about cognitive modeling of performance on the observer bet task, I'd like to first talk about learning. When we learn about the world, our learning process will often take the form of a sequence of repeated choices, which are not independent. How we select an action to take at each point in time is dependent on the collective results of our previous actions. For efficient learning, a general strategy we can employ is to transition over time from exploration to exploitation. When we explore, we try a variety of actions to see what the outcome for each may be. This will prioritize the gain of information, but at the cost of reward. Once we reach some threshold of certainty as to which actions are beneficial to select, we can switch to exploit actions. Now we consistently select what we believe is the best action in hopes of maximizing reward over time. However, in practice, this is a tricky balance to strike. How do people manage the explore-exploit trade-off? A good balance is even trickier to attain when which action is best can change with time, in which case one may need to return to exploration periodically. The main question I'll try to answer in this talk is, how do people manage the explore-exploit trade-off when the environment is dynamic and feedback is intermittent? Typically, we talk about the explore-exploit trade-off in the context of reinforcement learning. However, in a typical laboratory reinforcement learning task, exploration and exploitation are fundamentally conflated. For any given action, it's impossible to be sure of the motivation behind it. So how can we study the explore-exploit trade-off? Let's consider the binary prediction task, which is both very similar and very different. Now we have a box with two lights on it. The box is biased to turn one of the lights on more often, and it's your job to predict which light will turn on next. What if we tweak this task so as to separate learning about outcomes from the accrual of rewards? The observer bet task does exactly this by adding a third action, observe. This presents the opportunity to disentangle exploration and exploitation by making the motivation behind a given action unambiguous. Let's dig into this a little bit more. If you choose to observe, you can see which light turns on, but you forgo any gain or loss of points. If you choose to bet on either of the outcomes, you will be blind to what the box does, but now you get a point if you're correct and lose a point if you're incorrect. In this way, observe actions are made to be purely information-seeking, and so are explore actions, while the bet actions are made to be purely reward-seeking, and so are exploit actions. The choice to observe or bet is made on each trial within a 50-trial block. We only use the dynamic version of the task, in which the true light sequence has a change point when the popular and unpopular light colors switch, represented by the vertical bar here. So participants must figure out how to balance observation and betting to ensure they maximize their total reward across the block. Recent work with this task has assumed that the process driving human behavior is similar to that of an optimal agent. I'll talk about this Navarro paper a lot in this talk. And that reinforcement learning can't capture behavior on this task. But if we didn't make these assumptions, could we perhaps better describe human behavior on the observer bet task? And also, if we have a good working model, can that help us to better understand the explore-exploit trade-off? So Navarro and colleagues worked out the optimal solution to this task by defining the optimal agent as a Bayesian reasoner. Turns out that the full optimal policy is very close to a simpler policy, a Markov decision process where the state is the number of A events observed minus the number of B events observed. So this difference in counts, combined with the trial number, gives us the optimal probability of observing or betting on a given trial, as you see in the heat map here. From the optimal policy, they derive the optimal threshold, which we can use to simulate the behavior of an optimal agent. This agent will observe and bet when the accumulated evidence is between versus outside the thresholds, respectively. And you can see that this accumulated evidence decays over time. This allows the agent to occasionally observe again, and thereby react to changes in the environment. In other words, the optimal agent alternates between observing, or exploring, and betting, exploiting. However, you may note that the behavior of the optimal agent will differ from human behavior in some notable ways, namely that the optimal agent's bets are always consistent. You don't really see this in the human participants. Nonetheless, this was an excellent starting place for model development, and it helped Navarro and colleagues to develop a model of human behavior because it gives a sense of how the underlying process might work. It also suggested meaningful behavioral patterns to look out for, which we can judge the human performance against. So participants in our collected data largely did approach the task in the right way. They observed more at the start than at the end, and generally correlate their bets to the true light sequence. Oh, and this first figure has the data labeled as control because this data was collected as part of a larger clinical research project. Because that work's unpublished, I won't speak about the patient group today. Ideally, we develop a model that can not only capture a participant's rate of all actions across trials and states, but also one that it can explain their different explore-exploit trade-off strategies. You can see here that participants' ratios of observations to bets can vary a lot, and they exhibit some suboptimal behaviors, like the mixed streaks of betting, which we see in the two rightmost participants here. Participants' suboptimal behaviors include not always observing on the first trial and not always betting on the last trial. They also mix their bets in about 20% of their betting streaks that are longer than one bet, and they don't always bet on the last color that they observe. So the heuristic model that Navarro and colleagues developed is very similar in design to the optimal agent. You keep a running tally of the number of orange versus blue lights that you observed. You decay that evidence to cope with a dynamic environment, bet if you exceed the threshold, and that threshold decreases over time, hopefully in a way that mirrors the optimal policy, and also is allowed to be noisy because humans are noisy. Here's the full model specification as we did it in STAN. So Navarro and colleagues found that the model with evidence decay and with piecewise linearly declining thresholds was best able to account for their data. However, we found that the piecewise linearly declining thresholds required a parameter that was unrecoverable and pathological in the STAN implementation, so we included a new version of the model with just linearly declining thresholds. We also include models with and without evidence decay, and another new extension where evidence decay is allowed to increase over time. However, I wondered if people are really developing a strategy from scratch. Can established cognitive processes already explain this behavior? What about a model built from a Q-learning framework? Perhaps people are instead using existing cognitive process and adapting it to suit the peculiarities of the task at hand. If this was successful as a model, it could represent a meaningful extension of reinforcement learning models and theory, for example, by accommodating more realistic settings in which we don't always get feedback for every action. However, under a strict interpretation, reinforcement learning should not be able to capture observer bet task performance, a point which Blanchard and Gershman explicitly emphasize in their discussion. But by relaxing a few strictures, I successfully adapted reinforcement learning for the observer bet task by developing a modified RL model, which I will build up for you now. Before the first trial, we assign all actions, bet on orange, bet on blue, observe, a value of 0. On each trial, we either initialize or forget the values from the last trial. We convert the value into action probabilities with inverse temperature beta and use those to roll the dice on an action. And then here's the modified bit. Rather than learning from receiving rewards, which the participant doesn't see until the end of the block, we now learn from observations. The idea here is that when the participant observes, they think, I just saw the orange light, so if I had bet on orange, I would have earned a point. However, there's a problem here, namely that participants would never observe again after the first trial because the observe action's value was never updated. So I thought participants might be coming into each block with a high value already assigned to the observe action, as is captured by the QOBS parameter. Now when the participant bets, the value of each betting action will decay towards 0, while the value of observation stays high. This allows the bet's value to fall back below the value of observation again. I also considered a model where this boosted observation value decreases over time, and models with counterfactual learning in case participants are also learning from the outcome that was not observed. The idea is that if the participant sees an orange light, they not only think, if I had bet on orange, I would have earned a point, but they also think, if I had bet on blue, I would have lost a point. Here's some priors. I ultimately compared 6 heuristic models and 6 modified RL models, where the RL models include all possible combinations of the extensions that I just described. And the model comparison shows that the best modified RL model provided a better scoring fit to our data than the best heuristic model. Our winning model is the modified RL model with both direct and counterfactual learning, and with a decreasing, not updating, value assigned to observation. The posterior predictives for this model mirror the data extremely well, matching the action rates across trials and states, and capturing the suboptimal behavior rates. And also, this was the only model out of the set to nail the suboptimal observation rate on the first trial. So, what can this model tell us about how people develop a good balance between explore and exploit actions? First, we can see that individual differences in inverse temperature seem to predict suboptimal behaviors like mixed betting, which we don't really see for the other model parameters. Learning rates were generally high. This makes sense if participants are trying to maximize their encoding of the little outcome feedback they do get. But it's interesting to see that the counterfactual learning rate in particular is as high as it is, as this generally doesn't contribute that much to models of traditional RL tasks. So, counterfactual learning seems very important for learning from intermittent feedback. And finally, we see that the value assigned to the observe action declines across trials. And if we look at the estimates for individual participants, we see that at the start of a block, participants almost always assign a higher value to the observe action than to the bet actions, which are initialized at 0. So this can help us to explain individual differences in explore-exploit trade-off strategies. In an uncertain environment, we initially value exploration highly, as you see with the policy on the first trial here. We switch from explore to exploit actions as the expected value of a reward-seeking action exceeds the value of information gathering, and vice versa, as you see how the policy here matches the switches in behavior from observing to betting. And however, if we are insensitive to these value signals, then we begin acting haphazardly, as you see the uncertain policy causing the mixed betting here. So 2 points I want to touch on before I end. First, some implications for RL modeling. That the modified RL model was so successful here suggests that a broader interpretation of reinforcement learning is warranted. Under a very strict interpretation, which is not unpopular, reinforcement learning can only capture learning from rewards, meaning feedback that's objectively rewarding, like food. But in the observer-bet task, participants never directly learn from reinforcement. No reward feedback is seen until the end of the block. That reinforcement learning model can still capture this behavior, then suggests that reward processing mechanisms are likely also recorded for learning from outcomes. And so, simply gaining information may be perceived as intrinsically rewarding, even if it's not extrinsically so. And also on a larger note, there's a rich variety of cognitive processes that we use to guide our actions, especially in an uncertain world. Now, our model comparison showed that the process underlying performance on the observer-bet task is well described as a modified reinforcement learning, and still well described but a little less so as a novel heuristic process. Now, this makes sense if we remember that reward processing is a canonical neural computation, so perhaps we should view reinforcement learning as a canonical cognitive process. And through this lens, we can view our results as a case example of how, when presented with a new cognitive task, we select from the general purpose machinery we have and adapt it to suit our current goals, the environmental context, and so on, until we're able to generate the diverse range of behaviors that we observe in everyday life. So in closing, I'd like to thank my collaborators, especially Manon. This data comes from clinical research that she led. The modeling I contributed is just a component of that larger work. And for the MathPsych attendees, if you have questions or thoughts about the modeling, I would love to hear your thoughts at the live Q&A. Until then, thanks for listening.